Now we're going to talk about water as a solvent. We say that not always is water the solvent, but with a lot of the problems we're working with, water is the solvent. So we want to look at how water interacts with different types of compounds. We're going to start by talking about molecular compounds. Remember, those are the ones with covalent bonds. Well, some things will actually dissolve in water because they react with water. Let's take, for instance, HCl. HCl reacts with water. It actually goes through a chemical reaction. Remember, the bond in HCl is a covalent bond. So this isn't not a process like we had with ions where it dissociates into its ions. That's not what's happening here. What happens is that the electrons on the extra electrons on oxygen will take that hydrogen away from HCl. The electrons that are shared between those two then go onto the chlorine. And as a result, we end up with our chloride ion, and we end up with our water with this extra H on it. And that's called the hydronium ion. And once we have two ions, these are charged particles, and they're definitely going to be soluble in water. So HCl is soluble in water because it actually goes through a chemical reaction with water and forms new compounds at the end, or new ions at the end. So that's the way that some compounds get their solubility. Let's talk about other types of compounds and how they are soluble or not soluble. Well, let me start off with nonpolar. Nonpolar we know are not going to dissolve because we've got the term like dissolves like. And when we say like dissolves like, remember we're talking about polarity. So nonpolar are only soluble in nonpolar. And we know water is a polar substance, so nonpolar substances will not dissolve. You can think about if you're trying to clean up an oil spill, say you spilled some oil, cooking oil on the counter, and you try to clean it up with water, you're probably not going to get very far because the water and the oil just don't mix. Okay, so they are not soluble. However, if you have polar compounds, they will be soluble in water. And that is because of the intermolecular forces that will help solvate the molecule. Let's look at ammonia as our example. Here's ammonia, NH3. And what can happen is we've got these intermolecular forces that can develop between the water. So here's our partial negative charge of our water. It's got the lone pair on the end. And here's a hydrogen that's got the partial positive charge on the ammonia. And so this hydrogen bond can form, and it can form on the end of all of those hydrogens. Furthermore, the nitrogen has a lone pair, so we can get a hydrogen bond to water this way as well. So we've got this whole system of water molecules that can interact with the ammonia, causing this sphere of hydration, the sphere of waters around it. It's called the sphere of hydration. And that actually pulls it into solution, pulls it into the water so that it dissolves more readily. Okay? Always keep in mind, though, the negative end, partial negative, lines up with the partial positive, and the partial positive lines up with the partial negative. So you want to make sure that you understand which direction all of those bonds are occurring in. Now let's look at, we've discussed what happens with nonpolar, we discussed what happens with polar molecules. What happens if you've got a molecule that has both a nonpolar and a polar part? So in some cases, let's focus in on this one in particular. We've got a small nonpolar part and a polar part of the molecule. Well, the polar part of the molecule can have those intermolecular forces setting up, and that can actually cause the molecule to come into solution because it pulls it so that we've got that sphere of water around it. And this is our example of the solvation of methanol. Okay, solvation, the solvent, which is water in this case, actually pulls it into solution, and the methanol dissolves. Let's look at the second case where, say, our nonpolar section is so much greater than our little polar section. This is pentanol. It's got 5 carbons and then a little bitty OH at the bottom here. In this case, the nonpolar section is so much bigger than this little section that's polar. This compound is going to not be soluble in water, because the nonpolar one is so big, it's going to say, nope, not going to go into water, and it's going to remain insoluble. Okay? So when you've got these mixtures of 1 part polar and 1 part nonpolar, it really depends upon which part's larger as to whether it'll go into solution or not. Okay, so that was a quick review of our molecular compounds, those that have covalent bonds. Now let's look at our ionic compounds. Well, ionic compounds we would expect to go into solution because we've got that like dissolves like. Remember, charged particles and polar particles will dissolve in each other. So let's say we've got sodium chloride. The sodium chloride will actually go into solution and dissociate into its ions. So let's look at the sodium part. The sodium part is positively charged, and it's going to have interactions with the partial negative end of the oxygen. Okay? And then when we look at the chloride does the same thing. So chloride's negatively charged, and it can interact with the partial positive charges on water and come into solution. Each one of these has this sphere of hydration around it, where it's actually surrounded by water molecules. Okay. And with ions, it can be anywhere between 2 and 6 water molecules per ion that helps this hydration. Sometimes these water molecules are so tightly bound to the ions that when they come out as an ionic compound, they actually pull the water down with it. In these special cases, these are called hydrates. Okay? It doesn't happen with sodium chloride. Sodium chloride will come down as sodium chloride. But the hydrates actually pull water down. So in the crystals, the solid form of copper 2 sulfate, there are 5 water molecules in there for every molecule, for every copper 2 sulfate. So we've got a name for these. To name these guys, what we're going to do is we're going to name the ionic compound, we're going to put our prefix, and then call it a hydrate. Let's look at this example. So this is copper 2 sulfate. We're not done yet, because we've got to add this part. It's pentahydrate. Penta meaning 5, hydrate meaning that the waters are part of that crystal. Let's try another one. This is barium hydroxide, and then there are 8 water molecules. 8 is octahydrate. So with all of the naming of the ionic compounds, the covalent compounds, also make sure you know how to name these hydrates as well. And we use all of those prefixes that we're used to in order to name these compounds.